meeting. So should we be doing that?
Are you asking me?
Yeah, I mean anyone. Okay, I think someone has started the recording, so maybe I'll just go along.
All right. Yeah, no looking back now. Yeah, sure.
Okay. Yes. Good morning, everyone. Our speaker today, Neeldhara Misra, is a Srimati Amba and Sri V.S. Shastri Chair, Associate Professor in the Department of Computer Science and Engineering in IIT Gandhinagar. In 2007, she completed her bachelor's in science in three majors: computer science, mathematics, and statistics from Mount Carmel College in Bangalore. Then she pursued an integrated PhD in theoretical computer science from the Institute for Mathematical Sciences, IMSc, in Chennai. After graduating from IMSc in 2012, she spent the next 3 years at the Department of Computer Science and Automation at our very own Indian Institute of Science, first as a research associate and then as an Inspire faculty fellow. Professor Misra's research interests include the interplay of structural graph theory and graph algorithms, tools and techniques in parameterized complexity, computational perspectives on combinatorial games, voting mechanisms with a special focus on strategic behavior, and fair allocation of resources. On behalf of everyone, I heartily welcome Professor Misra to our IISc MSR seminar series. Over to you, Professor.
Well, thank you so much for your kind information. I don't know where you dug all that up, but thanks again. And all right, so I'm going to get started and talk about parameterized approaches to Kemeny Rank Aggregation, which is one of my favorite voting methods. And I think this may be slightly different from what was advertised in the abstract in terms of the proportion of time that I will spend on stuff that's very classical versus stuff that's recent. I just realized once I started digging things up, I found a few fun proofs. I think I'll be presenting a couple of things that are kind of old, but will hopefully still be entertaining nonetheless and provide some context. So let's see how this goes. So the rough plan is to, give you some background, tell you what the problem is about, and talk about some foundational results that kind of set the tone and motivate the need for looking at parameterized approaches and also approximation algorithms along the way. And so we're going to look at, again, like I said, a classical NP hardness result a little bit, because it's just impressive that this is an aggregation mechanism that turns out to be hard, even when there are just a constant number of voters involved. And it's not a crazy constant, it's just 4 voters. So I thought that's pretty cool. So I'll tell you a little bit about that and its connection with, again, a classical graph theory problem, graph algorithms problem called feedback arc set on tournaments. So that's a fun connection to explore as well. And again, a lot has happened in that space in the recent past, but I'll tell you about stuff that's a little more textbook material by now, but was pretty cool at the time it came out. I think it's, again, a fun technique to see in case you haven't seen it before. It's called chromatic coding and still useful for problems that involve for solutions that involve subsets of edges and graphs. So we'll take a look at that a little bit. And then I want to segue into this recent notion of finding diverse solutions. Unfortunately, the word diverse is kind of overloaded a little bit in the literature right now. So it may not be what you're thinking when you think about diversity. There's probably a few notions that come to mind already, and this may be a little bit different from what comes to mind by default. But tell you a little bit about some recent work that came out, which is about finding diverse solutions to the Kemeny aggregation problem. So that's kind of the plan. So right, so what we are looking at is this is rank aggregation. So what you have is a collection of rankings over a fixed set of alternatives. Of course, when I say rankings, I'm thinking about strict linear orders, but you could generalize this to partial orders or weak orders, allow for ties and things like that. But just for simplicity, I'll stick to rankings. Yeah. And what you want to output is a single consensus ranking. So again, for now, we will focus on the setting where we want to output a single ranking, and then we'll come back to when we talk about diversity, we'll kind of generalize this a little bit. But for now, the goal is to output a single consensus ranking, and of course that raises the question of what is a consensus ranking. So let's just look at an example, and I hope you've had breakfast, otherwise this might make you hungry. But let's just say that these are food preferences, 5 different people, and the rankings are such that the leftmost object is the most preferred one. So the first person, for instance, likes pizza over burger, over cake, over donut, over tacos, and so on and so forth, right? So suppose you're given a bunch of rankings like this. What does it mean to output something that's a consensus ranking? Well, before we define what we mean by a consensus ranking, maybe I can hint to some properties that you might want intuitively a consensus ranking to satisfy. So for instance, it might stand out to you that everybody positions the donut at the 4th place. So it may not be unreasonable to want a consensus ranking to also somehow respect this, because it seems like everybody agrees that donut seems to be the fourth most liked food item among these 5. That could be something that you would like to propose. And here's another thing that's probably not as obvious, but when I highlighted, you might notice that everybody prefers a cake over a donut, right? I'm sorry if that's not your that's not your take on this. And you can also see that there are varying degrees. For some of them it's touch and go, and for some of them they prefer the cake very much more than the donut. But nonetheless, everybody prefers the cake more than the donut. So it would be surprising if a consensus ranking decided to not respect this, right? So, this is a property that's called unanimity. If everybody agrees on something, then the consensus must agree with that agreement. So almost everybody will agree that you would want your ranking to satisfy unanimity. But of course, that's not the only property that you might want your consensus ranking to satisfy. You might want it to satisfy a bunch of other equally natural and innocent sounding properties. And this is sort of the axiomatic approach to identifying what we mean by a desirable consensus ranking. And of course, if you just wanted unanimity, it's not very difficult to come up with a ranking which is unanimous. In particular, you could pick any of the input rankings, and that would be a unanimous ranking. And this is in the spirit of a dictatorship, right? You just go with what one of the voters is saying. So a dictatorial rule is unanimous, but it's not a very interesting rule. It's arguably also not a very desirable rule. And it turns out that once you pile on your axioms and desirable properties, very soon you encounter a whole bunch of impossibility results and non-existence results, which basically tell you that you may not be able to ever find a ranking that satisfies all of these properties. So the axiomatic approach crashes rather early. And not sure if there was a question. Let me just double check the chat. Maybe not. Okay. So yeah, of course, please feel free to interrupt me if I'm saying something stupid or not making sense. I'll try to keep an eye on the chat every so often, but please also feel free to just unmute yourselves whenever you like. All right, so as I was saying, the axiomatic approach to defining the notion of a consensus ranking gate crashes pretty quickly because you encounter non-existence. And one approach that people have taken to defining consensus rankings is to say, well, what's the ranking that's as close as you can be to satisfying certain classes of axioms that you might be interested in. So that's sort of one approach, and that's not the approach that we will be taking. We'll be taking a slightly different approach where we want to find a ranking that minimizes some concept of dissatisfaction among the people who are involved here, right? So what does it mean, again, to minimize dissatisfaction? So let's go back to our example. We have a bunch of rankings here, and let's say we just propose a consensus ranking, right? And we want to think about, how satisfied is everybody with this proposal, right? So we ask everybody, well, what do you feel about this ranking, right? And this prompts this idea that you probably need some sort of a distance between rankings. You need to be able to evaluate, if I have a certain ranking in mind and you propose a certain ranking that's going to be that we're going to call the societal ranking or the consensus ranking, how do I feel about this? Probably need a way to measure how I feel about a given ranking versus my own, right? So again, there are probably a bazillion different notions of distances between permutations. The one that we are going to consider is the so-called Kendall-tau distance, or the pairwise descent distance. So here's how this is defined. You essentially consider pairs of candidates and you ask yourself, well, what are the pairs that the two permutations agree on, and what are the pairs that they disagree on? So for example, between the cake and the pizza, both of these permutations feel that the cake is superior to pizza, and that's the same with the cake and the burger and the cake and the donut. But when it comes to cake versus tacos, the permutations disagree. Okay, and you could do this for every pair of candidates in question, and you'll find that in this example, there are 5 pairs of alternatives, assuming I haven't made any mistakes here. There are 5 pairs of alternatives on which these permutations do not disagree, do not agree. So that's going to be our notion of distance, at least for total orders. I think this satisfies the traditional properties that you would want a distance function to satisfy. This is not the case if you were dealing with partial orders, but that's something that we can live with. So essentially what we want to do is come up with a single ranking that minimizes the total Kendall-tau distance from all the input rankings. This is also called the bubble sort distance, because you can imagine that, if you think of the ranking on the top as some sort of an idealized sorted order, then this distance is exactly the number of swaps that bubble sort would have to perform if it had to transform the ranking at the bottom to the one that's on the top. So that's why it's also sometimes called the bubble sort distance. And this notion of finding a ranking that minimizes this distance, indeed a justification for this notion of distance, I think was given by Kemeny back in the day. And I think this is an intriguing paper titled Mathematics Without Numbers. And, it's a nice read if you want to take a look at the backstory of how this notion of distance is justified and so on. I'll not get into it very much more. But what is interesting is that determining such a ranking that minimizes the total bubble sort distance from all the votes is, it turns out to be NP hard, and this was known way back in 1989 already. But in 2001, there was a strengthening of this NP hardness proof, which showed that this is actually hard even for just 4 voters, which has implications when you start looking at it from the parameterized perspective. So in particular, it does not make sense to parameterize this problem by the number of voters, because it's already hard when the number of voters is a constant. And again, we'll talk about the kind of parameterizations that this problem has been subjected to in just a bit. But before that, I want to just show you a glimpse of how this NP hardness result works, because it's, I think, really curious that something should be hard in such a strong way. Oh, sorry. It looks like I thought that I got disconnected, but that was from the Teams app. I'm so sorry. So I freaked out a little and tried to rejoin, but apparently I didn't need to. What I wanted to do is just check if there were any questions up to this point about any of the definitions. And I'll just pause for like maybe 30 seconds here, just in case there are any questions. Okay, it is a relief that at least I think I didn't lose the connection in the interim there. Okay, good. So yeah, and since there are no questions, I think I'll move on and maybe tell you a little bit about this NP hardness result, which basically says that even if you have just 4 voters, the problem of computing this sort of a consensus ranking based on this notion of distance turns out to be hard. Okay, and this reduction is from a problem called minimum feedback edge set. And well, of course, minimum feedback edge set just on undirected graphs is actually not even hard because so maybe I should first define what I mean by a minimum feedback edge set. It's the smallest number of edges that you need to remove for your graph to be cyclic. And if you have an undirected graph, then you sort of know that once you have removed your feedback edge set, you must be left with some sort of a spanning forest. So that's really all that you need to do. So this is not a challenging problem as it turns out, but it does become NP complete when you restrict your attention to directed graphs. And this is the problem that we will be reducing from. So just as an example, in this graph, there are perhaps 3 cycles in the underlying undirected graph, but the directed graph just has this one. If assuming I've checked this correctly, there's just this one directed cycle, and therefore you could get rid of it by removing just that one edge, and this is now a DAG. So so this is what you want to reduce from, and I'm not okay. So just as a disclaimer at this point, I won't be giving you the sort of the complete argument for the reduction, but just enough to sort of give you a flavor, because it turns out that the Kemeny rank aggregation problem has relationship that KRA shares with these graph problems that have to do with acyclicity. So I'll just try to convey a flavor of what's going on here. So the first thing we do is basically subdivide every edge. This makes things convenient, and it doesn't change anything as far as the solution size is concerned. So now we have all of these blue vertices which have in degree 1 and out degree 1. And what you do from here is I'm going to do this boring thing of labeling all the vertices so that I can refer to them. And I initially had this idea of color coding all the vertices, but turned out that I ran out of colors. So now there's just one that I've left in there, just so that I can, draw your attention to it if I need to. But based on this graph here, where basically all we have done is we've subdivided every edge in the original feedback edge set instance. What we are going to do is come up with 4 rankings which have which admit a solution of a certain size if and only if you can get rid of all cycles with a certain cost here. So that's the agenda. So what we're going to do is basically go through the vertices in order. And so this ordering is arbitrary. You can name the original vertices you like from, let's say, 1 to n. And then, of course, I've used letters here, but you can name the remaining vertices from n plus 1 to n plus n. And what we're going to do is basically start off with the original vertices and start listing out. To begin in the first ranking, we're going to start listing out their out neighbors. So 1 has no out neighbors, 2 has A, 3 has B and D, and so on. Oops. So for some reason, okay, I think. Okay, I think that, sorry about that. I think that there was probably an interim slide that was out of place. But yeah, basically what we are doing here is enumerating all the original vertices, and we are placing their out neighbors right next to them. At the moment, in an arbitrary order, I'm just following the alphabetical order here, and this may look a bit arbitrary. So we'll get rid of that arbitrariness in a moment. So this is the first ranking, and the second one, we do something similar. Except that now we list the in neighbors again in an arbitrary order. So we have 1 followed by A and B, and 2 followed by C, and so on and so forth. So you can sort of trust me that this is the in neighbor ordering for all the vertices. And now let me just put these two rankings side by side. At the moment, okay, I don't know if there's a whole lot of intuition in this example, but what you might imagine is that if the original graph happened to be acyclic, and if you had a topological sort on the original vertices, then one of these would completely align and would actually be in complete agreement with a topological sort being proposed as the consensus ranking, and the other one would have a certain amount of disagreement with a whole bunch of back edges going around. That's a little bit of a rough intuition, but of course it's not super helpful because first of all, we don't necessarily have a cyclic graph coming in. That's kind of the whole point. And besides, therefore, we have no idea about topological sort. Presumably, we want to be thinking about a topological sort once the feedback edge set is removed from the original graph, but we have no way of anticipating what that topological sort will look like. So basically, to make sure that we can actually work with no matter what topological sort is thrown at us, we need to get rid of the arbitrariness of choosing this order on the original vertices, which was just completely arbitrary to begin with. And that's where the other two rankings come in. So what we are going to do is essentially take the two rankings that we came up with and more or less reverse them. We're not exactly reversing them in the sense that, well, I mean, for instance, in particular, if you reversed the first ranking that we came up with here, you would start with the vertex I and then 8 and edge. It's not quite what we are doing. We're reversing them in groups. So what we're doing is we are taking the group of vertices corresponding to the last vertex first, and then we're putting in the vertex first, and then we are taking the list of its out neighbors and reversing that list. That's what we are doing. So it's more or less taking the ranking and turning it backwards or upside down, but it's just doing it a little bit carefully for reasons that, okay, so wouldn't quite work the way that you hoped if you simply reverse the whole list. This is something that I have checked at some point, but this slightly nuanced way of reversing the lists basically has it has a neat sort of a cancellation effect. So basically the idea is that if you have two rankings which are polar opposites of each other, so you have a ranking and you have its reverse, then it turns out that any other ranking will have a combined Kemeny score of n choose 2 from these two rankings when considered together, right? So n is the number of objects that you're ranking here. So for example, suppose you have 1 through 8 and 8 through 1. Let's just consider any other ranking. Just fix any pair you like. So for instance, 7 and 3. If this intermediate ranking ranks 7 ahead of 3, it's going to be in agreement with one of the rankings, but then just practically by the way the other ranking is constructed, it has to experience a disagreement with the other ranking. So any pair of objects contributes a Kemeny score of exactly 1. It must in fact agree with one of the rankings, and it must disagree with the other. So it turns out that with the construction that we just saw, there's a Kemeny score of 2 times n choose 2 plus 2 times m choose 2 plus 2m is completely unavoidable. So if you go back here and just look at the way the original vertices and the blue vertices are positioned, you can already anticipate that a score of 2 times n choose 2 and 2 times m choose 2 is completely unavoidable. There are n black vertices and m blue vertices, and the 2m sort of comes from the interaction between the black and the blue vertices, the way they are. That forces the Kemeny score of at least 2m. So what this sort of careful reversal of the original lists has done for you is that it's kind of taken away the arbitrariness of the initial ordering. It's forced a certain Kemeny score on any ranking. And now it turns out that if, for example, your graph was acyclic to begin with, then if you proposed the topological sort as a consensus ranking, then it would actually have this exact Kemeny score. It wouldn't have it wouldn't have any more suffering beyond what was the bare minimum. On the other hand, if you had a feedback edge set of size at most k, you can imagine that you have the topological sort, and all the edges in the feedback edge set are like these back edges that are going against the flow. And it turns out that the way those edges manifest in terms of like the Kemeny disagreements is like exactly fixed function of k. In fact, it turns out that each of these back edges contribute a Kemeny score of 2. So that's essentially how you would argue the forward direction. You say that you take the feedback edge set, you delete these edges, look at the topological sort that from the resulting graph, look at the topological sort on all the vertices, and you can sort of argue that this is exactly the Kemeny score that you're going to get from this consensus ranking. And the other way, it turns out that any sort that you propose, you can interpret it as sorting of the vertices, and the number of back edges will, again, the correspondence between the back edges and the disagreements in these rankings it turns out to be pretty clean. So the reverse direction works out in pretty much the same spirit. So I'm not going to belabor the details anymore here, but happy to talk about it more if you'd like to sort of pause and take a closer look. But this is sort of how you manage to show that computing the Kemeny score is hard, even when there are just 4 voters in the picture. Okay, so now let me try and make sure that my slides are ordered properly. Okay, yeah, so I think I wanted to tell you a little more about the progress on computing the optimal Kemeny score. So it turns out that, so if you remember, this strengthening of the NP hardness result was back in 2001, and there have been a couple of constant factor approximations since, which typically have relied on mostly LP methods. There have been a couple of combinatorial algorithms as well. Some of them have been in the spirit of generalized sorting algorithms, and there are quite a few elegant approaches out there. So, there's a 11/7 approximation algorithm that was randomized in 2005, and then there was 8/5 approximation. This, I think, was the combinatorial one, and this was deterministic, if I remember correctly. And then there was a PTAS in 2007. The PTAS was originally proposed for feedback arc set on tournaments. But notice that it's the weighted feedback arc set on tournaments, which means that that's actually equivalent to Kemeny rank aggregation, as we will see in a moment. And of course, I promised to talk about parameterized approaches. So these have been mostly the approximation line of work that I've talked about so far. So the parameterized scene has also been fairly active with respect to this problem. So just a quick recap of the terminology in a parameterized.
Yeah. Just a minute, Professor. Before we go on to the parameterized stuff, like there is a question in the chat box. Do you wish to take it now, or perhaps at the end of the talk?
Yeah, absolutely. Okay, so is all rank aggregation hard, or just the axiomatic approach that I described? Yeah, that's a good question. I think, the hardness that I'm talking about is definitely specific to the Kemeny method, or the proposal that we want a ranking that minimizes the total Kendall-tau distance from all the votes. You can imagine that you could work with different notions of distance. So there are many other distances between permutations that could be considered. If memory serves right, most of these methods do turn out to be intractable. I guess you could also, like I said, not think about distances at all, and so for instance, in an axiomatic sense, one of the things that's considered to be very desirable is finding a Condorcet consistent ranking, or finding a Condorcet winner, which is, so a Condorcet winner is a winner that beats every other candidate in pairwise elections. So if you just constrain the rankings to this candidate and any other candidate, they have that they have a majority in that restricted election. The thing about Condorcet winners is that they may not exist. So, but if they did, then you could sort of say, okay, I'll pick out the Condorcet winner and rank him first in the consensus ranking. That seems like a very reasonable thing to do, and just repeat the process. So I think there is a ranking notion which says that, okay, if you can't find a Condorcet winner, then what is the nearest collection of rankings which does have a Condorcet winner? And that's going to be that's going to give you some concept of a score. So, so as I said, for the axiomatic approaches that seem to lead to dead ends, you could adapt them to say, well, what is the best we can do in that context? But as far as I know, most of these approaches also turn out to be hard. But I'm not aware of a meta theorem which says that any reasonable aggregation method that you propose is going to be computationally intractable. As far as I know, there is no result like that, but most of the individual methods that I can think of do turn out to be intractable. But the one that I specifically talked about was certainly just limited to Kemeny aggregation. So I hope that addresses the question, makes sense. But let me know if you have any follow-up remarks there.
There seems to be another question as well from Rahul Madhavan.
One more question. I just wanted to know the approximation algorithms that you spoke about, they are approximate in which parameter?
Okay, yeah, good point. So they're all approximate in the Kemeny score. They're all trying to approximate this, the total distance from all the rankings.
Oh, okay.
Yeah.
Understand. Sorry.
Yeah, correct. Thanks. Yeah, good question. All right, so if there aren't any more questions, then maybe is it okay to move on, you think?
Yes, I guess we can move on.
Okay, perfect. All right, so yeah, right. So I think I promised to talk about some parameterized approaches. So as we just said, a natural parameter that you think about is the solution that you're after. But before I talk about that, let me just in case the parameterized framework something that you haven't seen before, it's a good time to slip in some terminology. So typically a parameterized problem is different from a classical problem, and just in the sense that you have the input as is usual in a classical problem, but you also have a parameter that tags along with it, and your algorithms are evaluated in terms of their performance seen from the view of this parameter. So it's a more fine-grained approach to evaluating the complexity of your algorithm. So if you can get an algorithm where you can divorce the running time of the parameter from the size of the input, and our typical worldview is that the parameter is nice and small, the input is terribly large. So we want something that's polynomial or efficient when it comes to input size, but is allowed to be expensive when in terms of the parameters. So so these kinds of running times, f of k times poly n, are called fixed parameter tractable algorithms. You could argue that even if it's n to the f of k, that's also a polynomial when the parameter is, for instance, a constant. Such algorithms are called XP algorithms, and they're not considered as nice because notice that the degree of the polynomial varies with the parameter, and that's whereas here you have a uniform polynomial bound, and hopefully the f of k running time is just something you can brush off in practice if k is small and f is manageable. So that's usually the goal. And the parameterized framework has also been useful for understanding pre-processing algorithms, which have mostly existed in the form of heuristics and such. But once you have this parameterized approach to problem solving, now you can talk about, you can actually measure how good a heuristic is by asking if the heuristic manageably brings down the size of the instance. So the goal with the kernelization algorithm is to run in polynomial time, and you're not necessarily looking to solve the problem, but you're just trying to reduce the problem or compress it to something that is of manageable size. And in this case, f of k can potentially be a polynomial function of k. And if you manage to get to that point, then you have on your hands what we call a polynomial kernel. And that's kind of the holy grail of efficiency in the context of kernelization. But there's also like a hardness framework which tells you when not to expect polynomial kernels. And there have been some relatively recent developments that talk about what's the next best thing that you can do when you don't expect polynomial kernels. And there have been a few attempts at sort of addressing that question. But I think the most successful one to date appears to be what is called lossy kernelization, which combines ideas from, again, approximation algorithms and puts them in the kernelization framework. So that's definitely a pretty exciting set of fairly recent developments worth watching out for. And there's a bunch of nice talks about lossy kernels on YouTube in case anyone's interested. All right, so Kemeny aggregation has been subjected to a lot of different parameters. The most natural ones would appear to be the number of voters and the number of candidates. And you could also think about the Kemeny score, which is the solution size. Folks have also looked at things like the maximum range of candidate positions, which is to say, you look at like the lowest that somebody is ranked and the highest that somebody is ranked. So you fix a candidate. And so let's say I have been ranked at the 5th position in the worst case, the 2nd position in the best case, and everybody ranks me somewhere within this range. So the size of that range for one candidate is the range of that candidate, and for the whole instance, you just max it over all candidates. So that's the maximum range. So this is a well-motivated parameter for classes of rankings that are likely to be kind of homogeneous, which is to say that people tend to have similar opinions about the alternatives. Then you would expect that the range doesn't fluctuate too much. Like most people have sort of a natural place, and there's a bit of you could think of it as like most rankings being a little bit of noise sprinkled on top of that natural position. Of course, there's a more formal way in which you could think about the votes essentially being generated by some noise model, but that's sort of a section of the literature that I'm not terribly familiar with. But I hear that the Kemeny aggregation method has a very natural interpretation in that setting as well. So once again, if somebody is intrigued by that, that's definitely worth checking out. So you could look at the maximum range or the average range, and you could also look at the Kendall-tau distances that are built into the instance. So you could look at the distances that the rankings have between them. And again, you could average them out or look at the maximum distance, and you could treat those as parameters. And I think pretty much all of these have been studied. As we already know, this problem is hard when the number of voters is even fixed. So that's not a very useful parameterization. And I think it turns out that it's also hard for the average range. But with respect to everything else, the problem turns out to be FPT. And yeah, there are some there are a lot of nice combinatorial ideas that go into many of these FPT algorithms. And there's also a bunch of kernelization-based approaches that's, again, quite nice and just leverages properties of structural properties of the rankings. But I do want to sort of again, segue a bit into the feedback arc set on tournaments problems. Is this cheekily titled paper in ICAL back in 2009 called Fast Fast. The first fast is like the English adjective, and the second fast is feedback arc set on tournaments. And this paper introduced, as far as I remember, the method of chromatic coding, which was a spin-off on the now classical method of color coding. And it led to some really nice running times. In particular, I think it led to the first sub-exponential algorithm for the problem. But of course, then I think some improvements started rolling in. So in 2010 IJCAI, there was faster fast, essentially, and along with other problems as well. And there have been a few updates since. I'm not like my aim is not to make this comprehensive here, but I would like to tell you a little bit about what is FAST doing in a talk about Kemeny rank aggregation. So, so the relationship is actually, again, fairly transparent. So let me tell you a little bit about that. So FAST is a problem about tournaments, simply complete directed graphs. It's a complete graph where every edge has an orientation. Yeah, we will come to the weighted version of the problem, but for now you could imagine that all the edges are unweighted. And of course, tournaments could have cycles in them. Our goal with a tournament, so imagine that this tournament is built out of, let's say, n players who have all played with each other in some round robin fashion. So everybody has faced off with everyone else, and these are the outcomes of the matches. And one thing that we want to do as humans is to sort of rank people according to, let's say, their competence or whatever. So let's say that this is a particular ranking of the vertices in the previous picture, and this is just the edges being redrawn. You can probably quickly tell that this is not the entire graph because it was a complete graph and the degrees here are falling short quite a bit. So these are all the forward edges with respect to this ranking. And you could imagine that these edges sort of are consistent with your experience of what you would expect, right? In the sense that if A defeats B, then you would want A to be ranked higher up than B. Okay, so assuming that the vertices on the left are the higher ranked players or candidates, these are the edges that are nice and that are consistent with your claimed ranking. But on the other hand, you also have these annoying back edges, which basically are reflective of what you might think of as upsets, where your ranking claims that A is better than B, but it turns out that B beats A when they actually played a match together, right? So of course, you're interested in finding a ranking that minimizes these upsets, minimizes the number of back edges that you have. So, so this is the natural optimization problem that you might be interested in. You could think of it as either the problem of coming up with a permutation of the vertices of the tournament where the number of back edges is minimized, or you could think of it as the problem of deleting at most k arcs so that the remaining tournament is acyclic. And again, a natural parameterization is by k, and there's actually a simple okay, so let me first actually tell you about the connection with the Kemeny rank aggregation problem. So back to our example where we are trying to figure out what's a good consensus ranking here. You can imagine getting a tournament out of this picture on the alternatives that are considered here with the following sort of edges. And now the edges have weights on them, and your goal is to, again, find an ordering of the vertices so that the total weight of all the back edges is minimized. So it's the natural generalization to the weighted version of the problem. And what we want to say here is fairly intuitive. What we want to say is that, for instance, okay, let's fix our attention on the burger and the pizza. It turns out that there's only one person who thinks that the burger is better than the pizza. That's the fourth person from the top. Everybody else thinks that pizza is favorable to a burger. Okay, so what you want to say is, well, okay, if you rank a burger higher than a pizza, then you're going to get yourself a back edge which has weight 4, because that's how many people you're annoying by making that choice. But if you do it the other way, you only get a back edge that has weight 1. And notice that if you have a unanimous pair, then you only have one of these two edges, not both. So that's because one of them, one of the orderings actually, you get it for free because everybody agrees there's no back edge to tell you that you've upset some people, right? So that's the sort of tournament that you can build out of the ranking. And now you could ask yourself for, weighted feedback arc set here, and that actually ends up giving you the optimal Kemeny ranking. So, so that's the relationship between. So you might as well be talking about weighted fast. That solves, in particular, Kemeny rank aggregation for you. This also has like a fairly clean LP formulation, which is pretty much the same idea. You have these Boolean variables XAB, which tell you if A is ranked ahead of B or not. It's And the first constraint here, well, actually, the constraint labeled 4 is the one that tells you that either A is ahead of B or B is ahead of A, and the QAB and the QBAs that you see in the optimization objective are precisely the number of people that you annoy when you rank them one way or the other. And the final constraint kind of forces some kind of transitivity to make sure that what you end up with, like the collection of pairs that is set to 1, actually correspond to a ranking, and it's not just some arbitrary thing. So, so whether you look at it from the ILP perspective or the perspective of the reduction, weighted fast and Kemeny rank aggregations, essentially the same thing. Okay, I see that I probably don't have more than 10-15 minutes left, so I'm going to skip through. Okay, I meant to talk a little bit about chromatic coding, but for that I would have to convince you about like a few nitty-gritty details here. Mainly that, okay, the first observation is that it turns out that you can actually focus on feedback arcs set by reversals as opposed to deletions. This is a bit surprising because reversals feel like a weaker operation compared to deletions, but it turns out that they're exactly the same. The advantage with working with reversals, where you're asking are there k arcs that can be reversed to make the tournament acyclic, is that when you perform your reversals, you still maintain tournament structure, which turns out to be useful in various contexts when you're doing stuff in your algorithms, right? And the main idea of so let me just skip ahead a little bit. Yeah, I think there's an easy observation that a tournament has a cycle if and only if it has a triangle, and that's the argument that I just skipped through. And so there's a simple branch and bound algorithm that gives you like a 3 to the k kind of a running time, immediately telling you that the problem is FPT. But it turns out that you can do better with it turns out that you can do better with this randomized technique called chromatic coding, where the idea is to sort of randomly partition the vertices in the hope that all the edges that are supposed to go into your solution kind of cut across this partition. And it turns out that a random partition actually has this property with a decent enough probability that sub-exponentially many repetitions of this make this a randomized algorithm with like constant error probability. So that's kind of the key technical statement that needs to be established. But once you have a partition that has this property that all your edges go across, it turns out that each part must induce a subtournament on its own right, because you have no degree of freedom there. You're not allowed to reverse any of the edges there. So each part must induce a tournament on its own right. And with that structure, it turns out that you can figure out the final solution using dynamic programming. If you look at the dynamic programming on its own right, it will appear to be expensive. So to get it all down to a nice sub-exponential FPT algorithm, you need to combine this with a kernelization algorithm as well. So there are a few different ingredients, but it turns out that they piece together really nicely to give you these nice sub-exponential algorithms. But in the interest of time, I'm not going to sort of get into the details of that. I want to step back for a moment and talk about this question of diverse solutions that I said has come up recently. So just to back up a bit, we often talk about decision problems where we're looking for whether there is at least one solution. And of course, there's search problems where we want to find these solutions. There are counting problems where we want to count all the solutions. And then there are enumeration problems where we want to literally enlist all these solutions. So these are the typical kinds of questions that we ask ourselves in the context of optimization problems. But more recently, folks have started talking about diverse. Well, I think I meant to say solutions here, but yeah, let's just say diverse, like the problem of finding diverse solutions. So again, informally, the spirit in which you ask this question is, can you give me, like, I don't want all these solutions, but at the same time, I don't want just one. I want to be able to choose from a bunch of solutions. So I think this was this as an idea has been around for a while, but I think it was codified and fairly thoroughly studied in a recent IJCAI paper, maybe 2020, I think, by a group of people who sort of actually gave a fairly generic framework for coming up with diverse solutions for various problems when parameterized by the structural parameter called Trevet. So they sort of had a meta approach to this, which was explained through vertex cover, which is everybody's, well, at least in the parameterized world, that's everybody's favorite problem. But then it was kind of generalized in a way that you could plug and play and get a DP-based algorithm for finding a diverse array of solutions. So maybe I should be a little more specific about what I mean by a bunch of good solutions or a good bunch of solutions. So essentially, you are demanding a collection of at least R solutions, which are all sufficiently different from each other. And again, depending on the problem that you're working on, depending on your solution concept, you may have various notions of distance. And you could also demand that every pair of solutions is at least d apart, or you could demand that the total distance when calculated over all pairs of solutions is at least some target. So this is usually what it means for a collection of solutions to be diverse. The idea is that they're sufficiently different from each other, right? So that's kind of what we're looking for. And yeah, so I think that the result that I wanted to talk about a little bit, at least, was from, again, this relatively recent paper titled Diversity in Kemeny Rank Aggregation, where you're essentially asking for not just one consensus ranking, but a bunch of them, which are all sufficiently different from each other, say with respect to the usual Kendall-tau distance that we have been talking about. So they actually work with a problem called the completion ordering problem, which should be quite reminiscent of what we just did with weighted feedback arc set. So here, the idea is that you have a bunch of elements and you're given a bunch of ordered pairs. And so that's a partial order that you're already given. I think it respects transitivity, I think. And now what you want is, so what you want is an extension of this partial order to a linear order that has minimum cost, right? And the way cost is defined is that for all the pairs that are not present, for every ordered pair that's not already present, you are given a cost of including that pair in your linear order. So there's something called the positive completion ordering problem, which is this restricted version where these costs must be strictly positive, whereas in completion ordering, you're allowed to have some of these costs being zero. And you can probably already see what this has to do with Kemeny rank aggregation. So you have your, you have the rankings, and what you do is, well, I mean, if there is a pair that is unanimous, you just add that in as a fixed pair. So for instance, everybody likes the cake over the donut, so we know that we want our consensus ranking. The Kemeny consensus is unanimous. It doesn't make sense to disturb unanimity, and that's hopefully reasonably intuitive. So you throw these unanimous pairs in as the fixed pairs that you want to respect. And for every other pair, you kind of know the cost of adding. So for instance, the cost of adding a burger preferred over a pizza is 4, because that's how many people that are there that don't agree with that. And the cost of adding the pair the other way around is just 1, and so on. So you add all of these costs, and you end up with an instance of the completion ordering problem. So the Kemeny rank aggregation problem reduces to completion ordering. And what's done in this paper is that they come up with an algorithm parameterized by the path width of the co-comparability graph of this partial order row that's developed from the unanimous pairs. So the co-comparability graph is, well, the comparability graph is just essentially the partial order. You have all the edges corresponding to the pairs that you have. And the co-comparability graph is, you can think of it as being the complement of this graph, right? And the path width is, I think this is a picture I've stolen from Wikipedia to show you what path width means. I don't think it's necessary to worry about the definition if it's a definition you haven't seen before. But just think of it as a measure of how close an arbitrary graph is to looking like a path, right? And it does have several, nice properties, and there's several nice ways of saying this. I'm kind of doing this a little bit of injustice here, but in the interest of time, I won't get into what path width is about. But I will say that one of the nice technical tools in the algorithm that's given here is to establish that you can actually come up with a path decomposition for the co-compatibility graph of a partial order that is in some sense consistent with the partial order itself. So if the partial order has a certain pair, then that pair has a nice behavior with respect to the path decomposition. So if the partial order says A is greater than B, then I believe the consistency guarantees you that the interval for the bags containing A does not end before the intervals for the bags that contain B. I could have potentially said that the other way around, but there is a natural notion of consistency that is exhibited by, or it is shown that you can come up with a nice path decomposition. Well, again, the word nice is used in a slightly different way, but okay, the correct thing to say here is that you can come up with a consistent path decomposition, and that actually ends up making the dynamic programming algorithm very convenient. I did have a couple of slides showing a little bit of how the DP works, but I ended up censoring it out because I did anticipate that we will not be able to get to it, but I will advertise the running time here, which is, it's some function of various things. I should probably at least tell you what all these symbols are. N and M are simply the number of voters and candidates. W is the width. R is the number of things that you're looking for. D is the diversity. That's the total amount of distance that you want between the solutions. And that these parameters delta and S, and I hope I didn't mix up the symbols, but delta and S are parameters that control some sort of a quality threshold. So if you so they actually solve a slightly more general problem where you're allowed to give up a little bit on the optimality of the consensus rankings to be able to get our rankings that are actually sufficiently different from each other. So you sort of have a tolerance, like a quality tolerance threshold that you can control, and that's where some of these other parameters are coming in. But overall, this is you think of this as essentially being FPT in the number of solutions that you're looking for, and the diversity and the path width, right? So that's one of the main things that came up. And also it turns out that the the positive completion ordering problem, which is actually more general than Kemeny rank aggregation, had so far algorithms of the form k to the k, where k is again sort of the cost of completing the ordering. And another thing that's shown here is that you can improve the k to the k to k to the root k to 2 to the root k, which is the kind of running time that you already have for special cases like Kemeny rank aggregation because of the connections with FAST and so on. So they do generalize that to PCO, which I think is sort of nice to know. Okay, so on that note, and I mean, I just in the nick of time, I think I will stop by saying that K-array is a fundamental problem that's also fun. It has nice connections with these graph algorithms. It's very well studied from both the approximation and parameterized lines of work. And I think it's probably a good time to see if there's plenty of, so it is a hard problem. As we saw, it's like NP hard even in a very restricted setting and so on. So there's definitely a lot of context for trying to see if you can do better if you look at combining the parameterized and approximation approaches, which is something that's being done a lot lately, but I'm not aware of that being done specifically for Kemeny rank aggregation. So I'll throw that as like one sort of, I think, fairly interesting direction for further work. And of course, the diversity work is fairly recent. And I think that while the path width of the co-compatibility graph is interesting, for sure, I think there's a lot that can be done in terms of understanding this parameter better, because I think it's a parameter that's small, again, for homogeneous. So at least that's my intuition right now. that you would want the co-compatibility graph to be sparse, which means you would want the compatibility graph to be dense, which means you expect a lot of unanimous pairs. So this works well when the rankings are fairly similar to each other. Would be interesting to see, what would be other things that make sense. So there are a lot of parameters that I didn't talk about, like closeness to single peakness and things like that, which I think would be also fairly relevant for the Kemeny rank aggregation problem. All right, sorry for going ever so slightly over time, but I think I will stop here. And if there are any comments or questions, that would be good at this point, I think. Okay, I see that there is a question in the chat. Do you want me to take that first?
Yes, please.
Okay, all right. Sorry, I think I should have caught this at the time that it came in. What does an equivalent instance mean? Does it mean having the same optimal value as the original problem? I don't remember in which context I talked about the instances being equivalent, but if it was in the context of any of these reductions that we did from feedback EdSet to KRA, or from KRA to FAST, or to completion ordering, in all cases, the equivalence basically means that this instance has Kemeny consensus ranking with a certain cost, if and only if the graph back there or the CO instance out there has a solution whose cost is typically, again, actually just k again, but in general it would be some function of k. But for the reductions that we did, I think the costs turn out to be exactly the same. Oh, okay. On the kernelization slide, yeah. Okay, so for kernelization, yes. So equivalent would be the traditional notion of equivalence, where you say that the instance that you obtain as the output of the kernelization algorithm is a yes instance if and only if. So this is all for decision problems. So it's a yes instance if and only if the instance that you started out with was a yes instance. So okay, so we are talking about decision problems in the classical notion of kernelization, but since you mentioned optimal values, as I said, lossy kernels is a more modern class of definitions, which accounts for also extending the kernelization approach for optimization problems. I'm pretty sure I will not get the details of the definition right, but they do have some sort of a way of translating the optimals and this the optimal solution. The idea with lossy kernelization is that you allow for the optimal to actually to actually change a little bit, but not by too much. And you have, I think, it's not enough to just have the kernelization algorithm. You also need a companion. I think they call it a solution lifting algorithm or something like that. So it takes a little bit of extra terminology to be able to talk about kernelization for optimization problems. But that is something that at least as a notion definitely exists in the literature at this point. But that's not what I was talking about on that slide. So those were decision problems, and the equivalence is just the boring notion of equivalence, where, yeah, that's hopefully that addresses your question. Thanks. Yeah.
Hi, so I had a question regarding, so you mentioned there's a PTAS for feedback arc set, right?
Yeah, feedback arc set on tournaments, weighted feedback arc set on tournaments, correct.
Yeah, so was that an EPTAS? Because that would directly imply an FPT algorithm, I suppose, right?
Yeah, it would. It's a good point. I don't remember if it was an EPTAS. Off the top of my head, I think not. But yeah, you'll have to allow me to. Yeah, I mean, we can go back and look at that paper. But yeah, that's a good point. I think the point here. Yeah, I'm not sure if the EPTAS would imply the kind of sub-exponential FPT algorithms that are known at the moment. But yeah, and also if we. Yeah, I'm not sure about the weighted version, but for the unweighted version, the thing about branching on triangles gives you a fairly intuitive reason for believing that the problem is FPT in the solution size. But yeah, I think yeah, it's a good point. I mean, you would get it by a direct implication. Unfortunately, I don't remember off the top of my head what the running time was. Well, it's a good point, and we can look it up. Yeah.
Right, and one more question regarding the runtime. It's 2 raised to root of some k, right?
Correct.
So that is allowed because k can be at most n square, and that would.
Yeah, that's a good point. I mean, this is a slightly sneaky choice of parameter in some sense, if you like, because typically for most optimization problems, you have some concept of the size of the object, and usually your optimal value is at most the size of that object. But in this case, the Kemeny score can be as bad as n squared, like you're pointing out. But in this case, yeah, I mean, I think the idea is that you've already given up on n as a parameter, and I'm not sure if the fact that the parameter can grow as large as, or can be quadratic in the number of candidates, gives you some intuition for why you would expect a sub-exponential time algorithm. But I'm pretty sure, like, I don't have an example off the top of my head, but the fact that the parameter is large will not definitely will not guarantee or imply. I'm not even sure if it gives you hope for a sub-exponential algorithm necessarily. But yeah, this may be one way of saying that, okay, all right, in practice, okay, square root of opt is still going to be potentially as bad as linear in n, if k is bad. So you might argue that, okay, I'm not as impressed as I would be if it was sub-exponential in a smaller parameter. So that I agree. But the parameter being large or being quadratic in some natural notion of size of instance, probably. So again, as I say, I don't have a concrete example to show that. So there are a lot of ETH and Seth-based hardness results which rule out sub-exponential time algorithms for a variety of problems. I would not be surprised if some of those involved parameters that were similarly large, but you still don't have sub-exponential time algorithms for them. So I hope that helps.
Right, and what if you had put a restriction on the size of the Kemeny score, like only in instances where it's, let's say, little
Yeah.
off n square or something? Maybe that's an interesting direction.
Yeah, that would be interesting. I'm not sure if, like, so there's been a fair amount of experimental work that's been done like in this kind of literature. So and that's work that I'm not super familiar with. So I'm not sure if there's something known from that line of research. But yeah, a lot of the kernelization arguments are driven by the fact that, okay, I mean, you have a budget for the Kemeny score, and that is k. In principle, k can be as bad as n squared, it can be as good as 0. But we are going to say that we have a working budget of k. So often what the kernelization algorithms will do is they will look at the, they will look at the rankings, and they'll say, there's so much drama going on here, there's no way that you're going to get a consensus ranking that has a cost of at most k. So just throw it out as a no instance. So having that k as a parameter gives you that flexibility. So like we said, if you have a ranking and you have its opposite, you are committed to a Kemeny score of n choose 2 no matter what you do, at a very minimum, if you have a pair of rankings like that. So if k is less than n choose 2, just, you just throw it out. Like that's m choose 2, and m being the number of candidates. So yeah, let's say you had a bunch of rankings which were sigma, and then n by 2 rankings that were sigma, and n by 2 rankings that were sigma reversed. Then you already know that if k is not sufficiently large, there's no hope. So the kernelization would just have the liberty to throw out these instances and say, we don't care. Like these are easy no instances because you're on a tight budget. So that's what drives a lot of the kernelization arguments. But yeah, I like specifically looking at k in terms of n, I think would definitely be an interesting thing to do.
So would you say it might be possible that the problem is not in NP hard anymore for, let's say, a slightly lesser size of k?
Okay, so right, you could argue that if k is like yeah, I don't know if that's implied by the kernels automatically, but yeah, I mean the FPT algorithms will tell you that it's polynomial for fixed k, right? So to that extent, yes, I think even for values of k, like let's say up to log square n, I guess, the FPT algorithm will kind of fizzle out and become polynomials. So yes, it's not hard for small values of k in that sense, for sure. And again, the intuition is that the small value of k restricts you so much that you can, I mean, either easily determine that it's a no instance or figure it out. But yeah, this is something that's more, it's a more generic thing. If you have a FPT running time, you can reverse engineer typically for up to what value of k can you push your luck, and that FPT running time will actually be polynomial. So with 2 to the square root of opt, something like up to log square n should be good.
Okay, thanks.
Yeah. Yeah, I will just like make a follow-up remark to say that sometimes people also look at the dual parameterization. So based on what you said, I'm also thinking about like, similarly, can you say that if opt is really large, like, so if I give you a very luxurious budget, very liberal case, you know, uh, pretty close to its maximum possible value, then you probably have an abundance of yes instances as well, because k is so liberal, you can probably also, so the dual parameterization would be something like, so the absolute maximum Kemeny score is something, let's call it T. So can you come up with a consensus ranking whose score is like at least K less than T, right? So I don't want to suffer all the way up to T. Can you give me a little bit of a saving? And that saving is codified as K. So, so again, dual parameterizations are a pretty common concept. I don't remember seeing it being a like, yeah, I could have missed something, but I don't remember seeing dual parameterizations being studied for Kemeny. So based on what you said, I think that could also be another interesting question potentially.
Okay, do we have any other questions? Okay, if not, maybe we can give a round of applause for the nice talk. Thank you so much, Professor. Thanks a lot.
Well, thank you. I mean, it was a pleasure being here, and apologies for running slightly over time, but it was wonderful being here, and hopefully see you at IISc sometime in person. Yeah.
Of course, the pleasure is ours.
Yeah.
So I'm stopping the recording at this point of time.